Hi, in this demonstration I'm going to show an Internet of Things and IoT use case demo where I monitor the output of a network stream, the performance of a network, and I use machine learning and storage in order to check for anomalies and outliers in the incoming data set. My name is Martin Madsen. I have a PhD in experimental physics and about 16 years of experience working with sensors, data collection, data analysis, and all kinds of different predictive model buildings. In looking at IoT projects, there are a number of different ways in which companies are implementing IoT in order to improve their business model and optimize the use of their resources. And today, the demonstration is going to look at essentially the boundary between the optimizing asset utilization and reducing operating costs by looking at the resource monitoring. I'm going to be looking for cases in which a network is performing badly and might have some need of maintenance or repair. The overall structure of this demonstration is going to start with something coming from an IoT device and the semi-structured data being transmitted to a hub, where then I'm going to use machine learning and pattern recognition in order to understand what that data mean and how to use that to improve the efficiency of the resource. And then push notifications out to people that will need to make actions based on that data. This overall pattern of using the data to create actions is a similar pattern for a lot of different IoT projects. In this particular demonstration, I'm also looking at two other requirements. What I'm looking for is a project that uses open source structures and open source tools in order to run the IoT system. I also want one that will be scalable so that we can scale up from a few devices to many devices in a straightforward way. The data I'm going to use come from the measurement lab. I'm using their network diagnostic test. This is a publicly available data set. What the network diagnostic test, the NDT test, is a client, a particular user, will sit down at their computer and test their internet speed. And it sends a handful of packets up to one of the measurement lab servers, measures how long it takes for them to the information to transfer to the server, and then it'll turn around and send the information back down again to the client. And the key performance indicator in this system is the average round trip time for sending the data up to the server and then bringing it back down again to the client. And in this case, the shorter the average round trip time, the better the network connection, the faster the network is working between the client and the server. The demonstration today is going to use a handful of different steps. I'm going to start with historical data, and from the historical data, see what I can learn from the data itself, do a little bit of data exploration. That first step is then dictates what kinds of machine learning I use on the data, what kinds of insights I can draw from the data itself, and then what kinds of patterns that we can start to see from the data in terms of performance of the network itself. And from there, we'll bridge the machine learning into real-time monitoring, where we can take the past data and say we now understand how different clients operate and how they're functioning. And if the performance of a client ends up outside of the parameters that we've already established, we'll call that an outlier and then trigger an action based on that information. The information I'm starting with comes from the historical NDT data, and I'm starting with the year 2015 and pulling off about 15 months worth of data. I have the date time of every client-server network interaction. I have information of the client and server, their IP addresses. I know where the client geographical location is, latitude and longitude, and I pull off a handful of different pieces of information, how many packets were sent back and forth. And then the KPI is the average round trip time for this particular interaction. The data exploration, when I plot the network lag time for the events as a function of time on the left-hand side here, what I see is that there are the majority of the events take very little network lag. However, there are events that take anomalously long, significantly longer than the majority of the events, and the colors are a log scale. So these events that are brightly colored are taking a lot longer, and these could be potential network problems. However, when I plot the data on the global scale, I wanted to see if there's a correlation between distance from the server, and this is all looking at a particular measurement lab server in Atlanta, Georgia, in the United States. Does the distance from the server to the client determine the average round trip time? And for some of these data points, it doesn't look like there's much correlation, that there's some blue colored points which indicate a fairly good a fairly small round trip time, and then there's a couple of the bright colored points right next to them, indicating that this might not be a geographical issue as well as some kind of network interruption or some kind of momentary problem. On the other hand, there are some locations, for example, this group of locations in the top of South America, which are consistently in the higher network lag time. And it might just be that that particular connection to that client is regularly a lot slower than some of the other connections. So I want to be able to distinguish the difference between something that's a normal performance for a client and then something that is an outlier. And I'm going to use a simple machine learning algorithm to learn the typical performance for each location and then detect outliers. My outlier detection algorithm is asking the simple question, is a new point an outlier? I have some set of previous data, and this is the historical data. And it's important that I have this data in order to train the model. So asking the question, is a new point an outlier? I'm going to use a concrete example here to talk about through the statistics. So imagine that I have two previous data points, and those data points had average round trip times of 90 and 110 milliseconds, and the new data point comes in at 100 milliseconds. By eye, I can look at this and say that's right in the same range, so that shouldn't be an outlier. The first step of the outlier detection algorithm is to measure the distance from the current data point to previous data points, and I'm doing a single dimension just on the average round trip time. You can do a measurement of the distance in a multi-dimensional case, in which case the measurement of the distance becomes a little more complicated, and it depends on the normalization of the different distances. But in this instance, it's only a single dimension, so it's a straightforward average of the distance. So in our example, we're 10 milliseconds away from the first data point and 10 milliseconds away from the second. Averaging those two gives us an average distance of 10 milliseconds. And then what I want to compare this against is the distance between the new data point and the group itself. If that distance is larger than the group size, then it's possible that this new point is an outlier. Well, if I look at the group size for my example data, the group size is about 20 milliseconds, the distance between the two data points. And in this instance, my example average distance is less than the group size, and so I would say that this example data point is not an outlier. However, what if I look at a data point where it comes in at 1,000 milliseconds? In that case, my average distance to the previous data points is 900 milliseconds, which is significantly larger than the example group size, indicating that this might indeed be an outlier data point. In terms of the statistics, I can define a new data point being some measurement x. The previous data have an average, which I call mu, and a variance of sigma, or sigma squared. And what I'm looking at is the difference between the new data point and the average divided by the standard deviation of the data. And if that's bigger than some threshold, we will call it an outlier. And the threshold epsilon in most outlier detection algorithms turns out to be about 0.75, which puts about 75%, give or take, of the data that come in as not being outliers. And this is something that a user certainly can set what threshold, what's their outlier detection threshold. In order to continue to run this as data come in, we need to take that previous data point and we need to actually update the average, and we need to update the variance of the data so that we now have a new piece, and this is where the machine learning algorithm learns what each client does and how it performs. If there's a slow drift over time, the data average and the variance will adjust itself over time so that the new data points coming in won't be detected as outliers. So I take the historical data and slowly build over time a pattern that learns whether or not the data are outliers or whether it's normal for a particular client. I've colored the data plot so that normal data points appear in the orange and the outliers appear in the green. And early on in the learning, almost all the data points are normal because I'm building a pattern. I don't have enough data points to tell whether something is an outlier or not. And then as time goes on, there are two possibilities that we could either have large network lag times which are normal for the client, in which case they appear orange, or we could have network lag times which are large for a particular client, in which case they are flagged as potential outliers, indicating there might be a problem with the network. And it's an intelligent system. It adjusts itself over time based on the data pattern. So the IoT architecture that I'm using here is to start with information, data coming from the device. I transport it over the network to a device and event processing hub, and then we'll send that on to a results presentation. In this case, I'm going to use a dashboard to watch for potential outliers. The data source, I'm pulling the data from the measurement lab. Data store comes from Google's BigQuery database. I pull it via the Raspberry Pi and using that as my stand-in for my device in this IoT demonstration. And then it will send the information over the MQTT protocol to my hub, sending each event as I talked about earlier, information, geographical information, and the average round trip time. On the event processing side, I'm going to use the Hadoop system based on the Hortonworks data platform. There's a lot of advantages to using the Hadoop system. First and foremost is the fact that it's based on the Hadoop distributed file system, which is a low-cost, redundant, and reliable data management system. On top of the HDFS, the Hortonworks data platform has actually built a number of open source tools that enable straightforward access to the underlying data in the file system. Two of the tools we'll be using, we're basing our event processing on a Storm. This is Apache Storm is an open source platform for dealing with streaming data. And we'll also use the Hive tool in order to query data from the HDFS and understand what the historical data are. And then we'll actually also store the data back into the Hive database so that we can update the learning algorithm for future events coming from a particular client. The Apache Storm topology looks like this. We pull in data from the MQTT channel, and that is the spout for this data, for this topology. We have our first bolt in the topology is our outlier prediction. We draw in data from Hive, from the HDFS, so that we can see what the previous data for a particular client were, and then we can make predictions as to whether or not it was an outlier. We'll store the record back into the Hadoop system so that we can use it for future predictions, and then we'll use a real-time visualization. We'll stream the data to a Power BI dashboard. In this case, we're using Microsoft's Power BI as a straightforward visualization of the outlier data. The actual Apache Storm topology has a few more pieces to it because I am transforming the data from one form to another as I'm shifting it to Power BI and to Hadoop via the Hive bolt. So there's a little bit of translation of the data coming in from the spout and then heading back out to the different clients. The topology in terms of Java pseudocode is straightforward to build the topology. We start with a spout where we use the topology builder and set the spout to connect to the MQTT protocol. The number of spouts and bolts, which is the number on the far end, is the way in which Apache Storm scales. Right now I have it set at 1 bolt, and in order to scale the system up, I just change the number of spouts and bolts, bolts that I have deployed in order to handle larger streams of data. That will require changing the infrastructure. However, if I deploy this Hortonworks data platform on a cloud server, and then it's straightforward to increase the capabilities of the system just by spinning up more virtual machines. I send that to a process bolt where I process the data and I connect. This is connected via the spout ID, the MQTT spout ID, and I group this by field, and the fields are coming in as the client. And then I send it via client subnet to the Hive emit bolt, which processes the data for then sending to Hive and storing the data in the Hadoop file system. And then I do the same thing. I process the data for Power BI and then send it to the Power BI bolt, which then sends it to Power BI Stream, which allows for live streaming of real-time streaming of data on one of their dashboards. And then the last step in the pseudocode is to do a submit topology, which then creates the topology. Because this is a straightforward system, it's also straightforward to expand on and adjust. If we want to add more capabilities to our system, I just need to come into the topology builder and add those capabilities. What I've got here is a recording of data coming from the IoT device. Each of these is a time aggregate data. I'm taking all the events from a day and compressing them so that I'm sending essentially one data point per second. So I've taken a day's worth of events recorded on this server, and I can send them in the matter of about a minute or so through the IoT hub. On the Storm debug monitor, I can watch the data coming in through the debug monitor and see each of the steps as it's bringing the data in. It's processing it through its topology and then it's sending back out again. Each one of these pieces talks about how the thread is looking at the data and how it's partitioned it and send it back out again. From this point, I send the data on to Power BI, and I'm using the Power BI Developer Center, and the way in which Power BI interacts via streaming data is that I start with my choice of technology. In this case, it's the Java-based Apache Storm streaming output. I authenticate via the Azure Active Directory so that I am connecting securely to the Power BI dashboard. And then I use a real-time updates and then present it as a dashboard in Power BI. Power BI has a number of REST endpoints that enable me to get the dashboards that are available on my account, and then I could post rows to a dashboard. If I know the dashboard, the data set name and the table name, I can then post the data. So this is a recording of event streaming in Power BI. I've got one data point per second coming in, and I'm looking at the geographical location. The green color indicates that the data are coming in normally, and the red color indicates that there is a potential outlier. The larger the circle is, the more total aggregate round trip time I have. So some events are happening in locations that had previously received data, and so the circle just changes size slightly as the data come in the same location. So I can envision someone, a network monitor, watching the real-time data as they come in, noting events and noting the persistence of outliers. Some outliers are due to simple hiccups in the network and come and go in a fairly quick manner. What I'm more concerned about are network outliers that persist over a small period of time, which might indicate that there's some cable breakage or downtime in some server somewhere. But those would be events that would then be noticed through the dashboard and then dealt with. The Power BI map updates itself dynamically, and I have this in batches of 10. So it sends 10 data points into Power BI, and then it refreshes the data set and starts over again, which is why the map resets itself about every 10 data points. So in summary, I start with an IoT data source. In this case, it's network data from the MLab data set, and send via Raspberry Pi over the MQTT protocol to my Storm Streaming Analytics platform, which is all open source data. It's open source code. I just pulled a handful of different libraries off of a variety of different network sources and compiled them together on the Hortonworks data platform in order to build this solution. I send the data back out to store the data and data streaming, and it's scalable and expandable both in terms of the capabilities of the system to deal with larger amounts of data by increasing the number of spouts and bolts on the hardware itself, as well as expanding capabilities. For example, a simple expansion was to set up a Twitter feed so that in the event of outliers, I had the system send me a notification, a personal message on my Twitter feed indicating that there was a potential problem and the latitude and longitude and the date time stamp. Like I said, I used a lot of publicly available resources, and if you're interested in building this kind of system, I've listed a handful of resources here. And thank you very much for listening, and if you have further questions, comments, or interested in further conversation, please feel free to contact